and thanks for the opportunity to be here. What I'd like to do in today's talk, we're going to cover a lot of turf, and I'm going to move really fast. If you want to stop and ask questions, that's fine. We can spend the time however you like, and I'll try to do my best to repeat the questions as they come. For those who are not physically here, if I forget, please flag me, and I'll try to make the questions clear. So the project that I'm going to talk about, the Synchronized Multi-Sensor Integrated Learning Environment, is actually a conglomeration of a number of activities that we've had going on at CMU for the last 4 or 5 years. So I am at the Silicon Valley campus, which is located in NASA Ames Research Park. We have about 400 students, more or less, depends on which semester you're talking about. And of course, we don't have all of CMU here in Silicon Valley. We have a thin slice. And it's 3 departments: electrical and computer engineering. I'm affiliated with them, the Information Networking Institute, and the Integrated Innovation Institute. So ECE in Silicon Valley is not all of ECE either. We are a slice of that, and the expertise among the faculty who are there are mostly in the realm of Internet of Things, wireless systems, sensing, privacy, security, things that are generally related to the Internet of Things, as well as software engineering, obviously related as well. And then in the other departments, product management, software management, entrepreneurship. So we have a habit of creating bi-coastal programs where students really have the experience to go back and forth between the main campus and Silicon Valley, and that seems to be working pretty well. So what I'd like to do by way of motivation is to give you some observations that I've made that I think may bear on this topic of how sensors and the Internet of Things may come to be. I'll admit up front, I'm not an adherent to what a lot of people talk about for the Internet of Things. My view of what it's going to be is actually rather different. And there are some big ugly problems that stand between us and that vision of the future, which is for a researcher an opportunity, right? So wireless systems, wireless technologies, sort of generally, and the ones that I'm going to talk about today, really offer some great promise in it. So there's a lot of talk about smart cities, smart manufacturing environments, the smart home, and many of these things, as is true in early markets, prefigure what will be, but really what we know now will be set aside in favor of something else. So I'm interested in the something else. And so we're digging into what people are viewing as the smart city, doing prototyping and building systems, really not in search of the answers, but in search of the questions of what will stand between us and some real smart kinds of environments. The interesting thing that kind of starts me off is economic. If we actually imagine a smart city, it's likely that the sensing and actuation that makes up smart intersections, responsive traffic control systems, safety systems, whatever, are not going to be built by a single organization at a single time out of a single set of consistent components. In fact, it will be the opposite of those things. It'll be a federation of separately built, dissimilar systems owned and operated by separate people who have separate privacy and information ownership points of view. And in that is really the heart of a number of problems. So there are some key challenges that I am concerned about, and this is by no means a comprehensive list. But the emerging Internet of Things, as I see it, is a problem domain that, like many good engineering domains, has at its heart a really interesting, impossible problem. I think every good engineering domain has at its heart some impossible problem. And the impossible problem at the heart of the Internet of Things, as we're going to see, is power and energy. And many of the things that also are related trace their roots back to power and energy. So the high performance and computing and communications in small devices is an enabler for a lot of what we might be thinking about doing today. Tiny form factors will be sort of de rigueur. I think that a lot of the Internet of Things is going to be what we call lick and stick sensors, very tiny, physically tiny devices that therefore will be somewhat impoverished in terms of energy, but maybe not in terms of computation. But they do have to run at vanishingly low power levels. The ability to harvest energy is somewhat limited. We'll talk about that. And the onboard energy sources are, of course, limited by physics. So in addressing these challenges, we take on some new risks and things that might not be obvious from a technology perspective. So we did a little thought experiment with our friends at the city of Palo Alto and elsewhere, where we imagined a day in the life of the city council where a representative from some large three-letter company that I might have worked for in my past, now focused on services, comes knocking and says, Mr. City Manager, we'll be happy to make Palo Alto smart. We'll make it smarter if you'll only pay us $50 million and take on this load of software and sensors and so on. And the city manager puts his arm around the fellow from the three-letter company, takes him over to the water cooler and says, let me explain something to you. Last week here at City Council, we wrangled for 6 hours and we finally made a decision to buy 8 new stop signs. The week before that, we had a similar wrangle and we agreed to fill 30 potholes. At no point can I imagine in the future that we are going to give you, no matter how smart you are, no matter how good you are, no matter how realistic your promises might be, $50 million to make our city smart. Okay, so if you think that Palo Alto is an outlier in that, of course it's not true. Palo Alto is probably the city that a lot of other cities look to for guidance in terms of what they do. So that's kind of a chilling vision. For those of us who like to play in this world of cyber-physical systems, cyber-physical in the sense that we'd like to scrape information out of the physical world, turn it into a problem that we can compute with and somehow create value out of that. But the problem is that cities, as the recipient of this stuff, have personalities. And those personalities will actually get in the way of realizing the smart city vision, right? So the adoption of these new ideas is typically slow. Really, can we even think about making cities smart using a top-down approach where you go to the city of Palo Alto and offer $50 million? I argue that that's not where we're at today. And really, we should be looking more at enabling bottoms-up opportunities to exploit sensors and computation, cyber physicality, if you will, in cities. So how is that going to come about, and who would care about it? Who would help make it fly? So we'll talk a little bit about those things. So some implicit criteria for success, if we're actually going to do this, is we have to please our city managers. We can't tell them, well, we have to build a custom device for this application, a custom device for that one, and tailor this, and send in an army of service representatives to, no. The idea of smart cities, I think, is much more like integrating whatever it is that we do with the people who make, say, stop signs. Because cities already know how to buy stop signs, we said that, right? And they know how to install stop signs, and they know what the life cycle of a stop sign is. So we have to figure out that if we're going to make a city smart, any infrastructure elements that we would introduce to the city had probably better look, feel, and smell like the infrastructure elements that the city already knows how to deal with, okay? One of the popular examples that I like, and we kind of followed this one, is the bots dot. How many people know what a bots dot is? Well, that's good. In California, the more hands than not, because bots dots were invented by bots at the California Department of Transportation, hence bots dot. They were these little ceramic domes that you can still see on the pavement surface today, and they're there specifically because of weather-related problems in California. When it rains, you can't see the lines. So bots said, I could solve that by putting these little ceramic domes. Well, since that, it's evolved to something called a Stimsonite marker that has reflectors in it and so on. But that's something that a city already knows how to install, right? Pick your favorite city. There's probably a guy named Joe or Steve or Dan or Lyle who can do lick and stick sensing, right? He has a bag full of sensors and he knows how to take them out and stick them on the road. What if we could put intelligence in those dots and make them have the same lifetime as the dots themselves? That sort of offers hope. But with that comes, of course, the constraints of the small size of the device and what you could cram into it in terms of electronics and particularly battery, okay? So city-friendly integration typically means introducing technology that's invisible to the Joe or the Frank or the Fred or the Lyle or whomever who actually has to install this stuff in the city. Okay, and now the other problem is this. We've been studying distributed computing for how many years now? 50 years? This is the world's largest, ugliest, hairiest distributed computing problem because the numbers are staggering. Right? You're going to be programming 100,000 devices in a typical smart city, maybe 1 million devices in a typical smart city. They're going to be dissimilar, as we said, and federated. Many will fail, right? So we have all the fault tolerance issues to deal with. We have the physical distribution, we have latency, we have network communication, we have synchronization, which we will come back to. And if we really want to make cities smart, My hypothesis is we have to make programming a city no more difficult than writing an Android or an iOS app. Wouldn't it be amazing if we could create somehow the tools that would let the same 3 million people, or whatever the number is, who made smartphones what they are today by writing apps using their time, energy, and effort, if we could somehow give them the same facilitation of a software development kit and a reliable pile of hardware, if you will, that's no more difficult. Well, so that's a big leap, right? Typical smartphone, you're programming the phone itself. Maybe there's some cloud service behind it, but now we're talking about coordinating hundreds of thousand devices. So we have quite a long way to go before we have a mechanism for doing that. So these problems which are sort of immediately apparent when you think about deployment lead to some interesting technological challenges, and I referred to the power one. Let's take a look at some of these problems in a little more detail as motivations for this project that we call SMILE. So the first problem, here's a test. The first problem is called the Ohio problem. Does anybody know what the Ohio problem is? It has nothing to do with John Glenn's birth date. Yeah, it means only handle it once, right? And the idea is this: if we were to actually make devices in the Internet of Things, come on, if we're actually true to this idea of making devices in the Internet of Things truly have a low cost of ownership, not a low cost of manufacture, we have to understand that going out and servicing these million devices, replacing the battery, injecting new software, reorienting them so their antennas point towards some gateway is simply impractical, because the economics of doing that far outweigh the cost of the device, okay? So now we truly have the problem of sensors or whatever the devices are that we hypothesize putting in the smart city as being lick and stick, okay? So we can ill afford to send somebody out to adjust all of those devices. So this has some interesting corollaries if we actually believe that. Okay, if the economics of deployment and maintenance will wipe out the possibility of deployment, we're stuck with this problem. What does it mean? Well, first of all, it means that unlike writing software for some large social media or search engine company where you can literally change the software overnight and just with a knob say which percentage of my population is going to be on version 1 versus version 2, we really have to think more in terms of writing software and designing hardware for a mission to Mars, where once it's off the launch pad, there's not a lot that we can do to go change our minds about what it is. So that's a fundamental difference in the way we have to think about designing these things. The second is related to that. We have to pack all the sandwiches that we need for the mission, because there's no subway along the way where we can go get some more energy. And the point that I made earlier about energy harvesting, I think if you do the math, you find that energy harvesting may actually be good for extending lifetime, but it's not something on which we can fundamentally base a deployment of sensors that could go anywhere in a city, under shade, under bridges, whatever, okay? So pack your energy. The third is we have to think really hard about where we put the computation. So the world of wireless sensor networks over the last 20 years largely approached the problem of sense, compute, actuate by vesting very comparatively little software in the devices that do the sensing themselves. Instead, we have devices that sit on the wall that say over the network, it's 72 degrees, it's 72 degrees, it's 72 degrees, it's 72 degrees, and something on the other end of the connection looks for changes, okay? That's generally if your network is wired and you have enough capacity to waste on some server to listen to this mindless prattle, that's fine. But if you're a wireless device and you have to put energy into every bit that you push over a noisy channel, all of a sudden you start asking the question, do I really want to do that? Do I really want to stream the values from the transducers to the cloud, where I have infinite computing and infinite storage and so on? Well, the problem is you don't have infinite energy to invest in pushing those bits over that noisy channel, okay? So where do we draw the line? Yes, sir?
Your microphone is dropping in and out.
Yes.
I recommend that you switch to the microphone on the...
I will try, but I will. Okay. So where do we draw the line? How do we think about where do we draw the line? Well, the way that I think about it, just from a very simple-minded perspective, is the stuff out of which we make this Internet of Things stuff are systems on chip. Inexpensive, increasingly dense devices that we can fill up with software that can do some sort of processing and do the data communication as well. Well, but those two things are actually quite different from an energy management perspective. If we imagine the evolution of these systems on chip over time, okay, as the technology for the SoCs gets better and better, what's going to happen to how much computing we can put on the device versus how much communication we can do? Well, you can believe what you might about Moore's Law, but at the bottom where we have these little Internet of Things devices, there's actually quite a lot of room to continue to improve them so that the same computation that you run today on your little IoT device, be it an FFT or moving average filters or what have you, is going to cost less in next year's chip in terms of energy to run it than it does today. That's actually a reasonably good bet. As time goes on, the cost of doing local computation is going to decline. What about the cost of communication? Well, if we believe that we know how to code information and send it over noisy channels, we can't push beyond the Shannon limit. Okay, so there's actually a hard physical limit that says you're never going to be able to code better so that you can push more bits from the device to the cloud. You'll hit a floor. Now those curves cross, and it says something actually quite interesting, that for some applications, say today, doing the computation remotely might result in less power used on the device because you're doing something that would require, it's more complex computation than you could afford. It's cheaper to send the bits over the air in an energy sense than it is to compute them locally. But as the devices get better, the trend is clearly in the direction of doing the computing on the device. So we now have the energy economics voting in favor of more distribution of function, which means more programming complexity. But the benefit that we get from it is a longer lasting battery or more complex computation that we can do in the sensor network. So that's kind of interesting. So energy concerns push us toward local sensing. Just to put some numbers on it, if we look at what is today a typical IoT device and the battery that might power it, say 1,000 milliamp hour lithium thionyl chloride battery, and we ask the question, if we want a device that's powered by such a battery to last for 5 years, and we make some simple assumptions about the battery self-discharge and so on, how much energy can we put into each of these basic operations each hour? Computing, transmitting, receiving. Well, it's not pretty. So sensing and processing in today's math, you get about 30 seconds worth of that on a modern SoC, and 5 seconds worth of receiving and transmitting. And next year, you might be able to get a little more sensing and processing, but the receiving and transmitting, as we said, are not going to get a whole lot better. So, and most of the time, of course, during that hour in the life is the device is totally asleep. This says a couple of things. One, as we said before, we really have to think very differently about this kind of computing. It's asleep rather than awake. And the second is that we don't want to waste transmit receive power on network protocol overhead or anything else that's non-productive, and so we call this the power challenge. And that's the big, deep, ugly, nasty thing that based on the IoT assumptions of how we'll deploy really pushes us. The second factor, second thing that we have to consider is time synchronization among these devices. If we want to be able to synchronize sensing in an environment, we have to have some basis for deciding when two or more sensors in an environment sense some quantity, and we want to correlate those in the cloud. We have to have a basis for deciding that the values that they've reported with timestamps on them can in fact be correlated. Well, is that a reasonable assumption? Turns out that just running a clock at reasonably high precision consumes a significant amount of power. So now we have to concern ourselves with the trade-off between what timing accuracy does the application require and how much of the battery power are we going to put into maintaining an accurate clock, okay? We'll come back to that. So different applications, of course, have different levels of synchronization requirements. We did a project for the U.S. Geological Survey where we built some software for smartphones, or at least demonstrated the principles for doing that would allow us to do early earthquake warning. And the idea is this: no, it's not detecting, using the accelerometer to detect shaking. What we're looking for is correlated ground movement across a number of phones in a geographic area. right? People who worry about earthquake sensing, this is interesting. People who worry about earthquake sensing think in terms of time scales from 1 to 100 seconds with physical displacements on the order of 1 to 100 centimeters, okay? So we're really looking for Route 880 going like this. So we'd like to know, of the phones that are on Route 880, are they moving in a direction that doesn't align with the directions of travel of the road, okay? Well, it turns out that that kind of correlation with the timescales that we care about don't require tight synchronization among the phones, right? That's kind of a good one. Well, as you move down the scale to what else you might want to sense, correlating, say, video frames from multiple cameras in a security setting or from drones or whatever, now you'd like frame accurate synchronization. So now you're down in the realm of 10 milliseconds or so. More interestingly, if you want to do something like taking simple sensors and using them to do acoustic detection, where I try to determine which direction Andy is using not my eyes but my ears, I need, in order to do the angle of arrival computation toward Andy, I need to be able to sample and correlate those audio samples down to about 5 microseconds. All right. Cheap device that can do audio detection and returning values and waveforms to me, but I have to put a lot of power into the clock to make it run well enough synchronized so that, you know, a 20 microsecond error is going to mean that I'm thinking Andy's over here instead of thinking that he's over there. So the application determines how much power we have to put into the clock, okay? That's the time challenge. The third thing is, as we said before, these sensors are not going to be built by some monolithic installation strategy. It's going to be many sensor systems that will be integrated after the fact. And we have to, there's a lot to be said about that, and I'm going to have to skip some of that for the sake of time today. Now here's the programming problem. If we think about programming a network of Internet of Things sensors, obviously we have to do the embedded programming for the device, okay? That's clear. And we probably have to do some cloud computing to aggregate that data, put the data in a database, build some nice visualization tools or whatever. And all along the way, we've got this, we've got billions and billions of dollars worth of networking equipment, cellular or whatever, that really don't contribute to the problem of doing the computation. Well, that's a sad fact. It may be changing as edge computing becomes a thing over the next 10 years. So we have, I'm sorry, I can't wander. We have at the bottom of this pyramid smartphones and Fitbits and things like that that are embedded, that are programmed in an embedded sense. But now we have to correlate that program with whatever goes on in the cloud. I can attest that from firsthand experience doing that and keeping the code bases and the header files and all of that stuff synchronized is a hard enough problem. But doing anything more intelligent like figuring out, having these devices self-describe their position and having the cloud software respond accordingly is actually a pretty hard problem. And it's a lot to put on, programmers. So what would be great, what we don't have today, is a mechanism for expressing, say, an application for a smart intersection that'll correlate information from pavement sensors and stoplights and cameras and the Teslas and Priuses that go whizzing through the intersection and somehow deduce from all of that information that a collision is imminent. But we don't have that. This, I believe, is the linchpin to doing what Apple and Google did for the app model. We need some way of letting programmers write one program that somehow gets decomposed into bits that run on the cloud, on the device, and possibly in the network. That can be that their correlation, their testing as a unit can be thought of as more of a single system. So we don't have that. That's the programming challenge. So if we think of those 4 challenges that I've talked about, they're actually pretty well interrelated. I think we've already talked about how programming and power, programming time and power, programming and federation all have a connection with one another. So really we cannot address the problem of how to build the architecture for the Internet of Things by looking just at devices or just at time synchronization or just at information sharing and XML dictionaries with matched keys that let us correlate temperature information from 2 different sensors that were made by 2 different manufacturers. It's really a system problem, and getting it right requires sort of a combined effort of recognizing problems, attacking them, building prototypes, deploying them, and then figuring out what question we really should have asked, and then doing the lather, rinse, repeat kind of cycle. So these, we really have a platform kind of challenge. Now, Andy alluded to the fact that in my background, in my dark, I'm sorry, thank you. Andy alluded to the fact that in my dark past, I had some relationship with companies that made big computers, right? I worked for IBM for 14 and a half years. And it scares my students to death when I tell them that they can go down to the Computer History Museum and see an IBM mainframe that these two hands built the arithmetic logic unit for. But you know, maybe not enough gray hair. I don't know what it is, but they, but it's true. I did work on big iron in the past. So I'm going to tell you a little story and a conclusion. I'll start with the conclusion, then I'll give you the story that comes from having lived through several eras of platform computing. And I think it has something to say about how we build the platform for the Internet of Things. Okay, we're going to start off with Iannucci's law, humbly named after your speaker. And Iannucci's law says that in each generation of computing, the emergence of a standard platform transforms the industry by shifting value, read money, from hardware to software to services. Okay? And I see some heads shaking. Okay? And some skeptical faces maybe in the audience who haven't lived through this. So let's actually go through this. Yes, sir.
Well, you can add one more.
Which is?
Content.
Yes, that's true.
Hardware, software, services, and then content.
Good, good. So let's engage what I call some marketecture thinking, and look at the market architecture and see what it can predict about the future. Okay. So here we have 4 generations of computing: mainframe, mini, PC, and mobile. And I worked at IBM in the mainframe era, and I worked at DEC and Compaq in the mini era, and I worked for IBM, although you know, it was still sort of a mainframe company. I was fighting with the senior management to get them to embrace this idea of personal computers. I learned that Dennis was the Tiny Basic guy. That's very cool. So I was alive and kicking during that area. And then, of course, I was at Nokia during its heyday in the mobile era. Okay? So I sort of have seen this movie, and there's a pattern. I'm going to share the pattern with you. So in the early days of mainframes, there was the bunch. Everybody remember the bunch? Burroughs, Univac, NCR, CDC, Honeywell, bunch, right? And in those days, this is in the 50s, computing was a priesthood. And we know that computing was a priesthood because of the language that we use. When we talk about running a program on a computer, what did we do? We submitted our patch job, right? So literally, we took our deck of cards and brought it to the priests who were on a raised floor, and we submitted our job. Okay. In those days, the value was clearly in the hardware. The hardware was dissimilar, and then an amazing thing happened. In 1964, IBM said, you know, it might actually be a good idea. And this is the 704 and the 7090 and the 1401. IBM had these glorious, wonderful machines, but they had a problem. Customers who had a 1401 who wanted to upgrade faced the problem of having to rewrite their software, and this slowed down sales. So the IBM geniuses in those days said, wouldn't it be cool if we could have sort of a line of computers that all run the same software? They were thinking instruction set, and we could just let customers buy up, right? We would build a scalable range of machines that would address this, that would be programmed using this instruction set. And over its history, I've kind of lost track of it now. The IBM 360, not only was the basis for IBM being taken to task by the Justice Department for potential monopolistic practices, because we had 70% of the market, but technologically it engendered a series of machines that spanned a performance range of more than 100 to 1, probably approaching 1,000 to 1. So that's like 30 dB dynamic scaling. That's not bad for a platform architecture to live and to span that kind of range. Okay. So by making the hardware standard, IBM did 2 things. They took the discussion of I can't upgrade because I have to rewrite off the table, which was good for IBM economically. But what else did it do? With this commonality comes commoditization. When you say all machines are created equal, all of a sudden the differentiation kind of vanishes and it becomes a race to the bottom, right? So what happened then? Well, Gene Amdahl went off and did his own thing, and Magnuson was formed, which I think was Gene's son, if I'm not mistaken. Plus the Fujitsu guys went off, and they all said, okay, IBM is going to dominate the world with this 360 instruction set. We'll just copy it, and we'll make machines that do the same thing, and we'll sell it for 20% less or what have you. Well, that's kind of interesting. And so the laws of economics took over, and all of a sudden, people were talking about not the hardware, but the next harder problem, which was building the software. And CSC, probably the young faces in this room, there aren't too many, never heard of CSC, okay? Billion-dollar software company that came to glory in the 1960s when the value sort of shifted from the hardware toward the software, yeah? And then toward the end of that era, the CIO said, you know, I don't want to deal with CSC on software and Amdahl and the leasing companies, which IBM hated. The leasing companies would buy IBM equipment and lease it, which took the wind out of IBM's sales. So IBM found itself competing on a hardware basis, didn't like that. But the CIOs didn't like it either, because now they had all these hardware choices. It used to be that, you know, no one ever got fired for buying IBM. They would just buy the IBM mainframe. They would get IBM to consult on the software. When this world changed out from underneath them, they didn't want to do that. So they said, you know, maybe what we want to do is we just want to buy a service. And through that service, somebody else will figure out what machine and what software, and we'll just, you know, we'll buy a payroll service, okay? So again, IBM came around and said, you know, services, that's actually a good business. Maybe we should be moving away from the big blue boxes because the value in the market has shifted, okay? So that's end of movie, trailers roll, you know, post-trailer scene and all the stuff that we expect. Mini computer era comes around, the Massachusetts miracle, right? Prime, Apollo, Wang computers, remember Wang word processors? DEC, Data General. And it wasn't exactly the same thing, but it was pretty close when when Ken Olsen said, "Let there be VAX." And what happened with VAX, and of course the contributions of the Unix community, we now had what looked like a platform computer. You could get big ones and little ones. You could not worry so much about the hardware, but what it did do, not so much in cloning the computers, it generated a huge market in hardware for all the disks and peripherals that plugged into the VAX mainframe. Remember Emulex, right? So they made a lot of money in that marketplace. So the value then started to shift from hardware to software. And of course, Oracle decided, well, we'll have a database, we'll let run on every machine on the face of the planet so that the people who want to run a database don't have to think about the hardware. And then EDS stepped in and said to the CIOs, we'll manage this whole thing for you. All right, not to belabor the point, PC era was a golden age of hardware. IBM said, let there be PC. Consolidation of the industry, Compaq became $1 billion company faster than any other company in history, doing exactly what the last two runs of the movie said that they should do, which was take the offered platform standard and make it cheaper. Microsoft, of course, made its fortune realizing that the next step in this era was the value shifting towards software. And what happened at the end of the era? IBM came back and said, we'll do the services. I was at Nokia in the days when IBM, we had IBM in Nokia for two reasons. One, we had 50,000 IBM laptops, right? Two, IBM ran our computing infrastructure. And I asked people, which do you think Nokia would rather give up? Would Nokia rather give up the 10,000 PCs and buy them from Dell or whatever, or would they rather have IBM replaced in running the payroll in the manufacturing facilities? And it was a horrific thought, right? Clearly the PCs were not valuable at all. What was valuable were the services that IBM had gotten itself deeply wedded to inside Nokia and in many other companies. So pattern, golden age, standard platform, value decline in hardware, shift to value in software, shift to value in services and content. Thank you very much. So how about mobile? Well, the standard platform for mobile, actually a little bit of a different beast, right? The standard platform for mobile is not an instruction set. It's an ecosystem, right? You've got the Android ecosystem, you've got the iOS ecosystem. And particularly in the Android ecosystem, we've seen a decline in the value that's associated with the hardware because it's a competitive marketplace, right? Huawei notwithstanding. So the question then is, if we've seen this movie 3.5 times and we know how it ends each time, what does it tell us about the Internet of Things? What do you think? Yeah. So the first thing that I say is, well, for the Internet of Things, we had better expect that there's going to be this golden age of incompatible hardware that we will largely throw out because it will be wrong. And that's where we're at today. And the next step, if you're a betting person, is to figure out what would bring about a standard platform for the Internet of Things. This is where a large sum of money is to be made, okay? So my hypothesis, not as a business person, but as a architect, an armchair architect, is that the next thing is going to be this cyber physical network. And what is a cyber physical network? Okay, it's an integration of two things: flexible, powerful, programmable devices, open device families, and flexible, powerful, programmable, open wired and wireless networks designed for the next 100 billion devices. And guess what? First one mostly exists. Second one doesn't exist at all. It ain't the cellular network, and for good reason, okay? So, is it going to, if that's true, is it going to emerge simply through an evolution of existing wireless networks? I think the answer to that is also no, okay? But let's talk a little bit more about what the attributes of this solution will, if we're to find a solution, what will its attributes be? First of all, it's got to face the fact that this world is distributed, federated, and energy poor. We have to be able to program it in some sort of a way that finally lets us separate answering questions of correctness. Is the algorithm that I've written for crash detection logically correct? Separate from the problem of where do I put the pieces of the problem? Where do I put the sensors, the computing, the data storage, okay? We should be able to do that, and there's been research projects in the past that have tried to do that. But now we have to do it for real, and we have to do it in a large scale. Otherwise, and I'm making a strong statement, if we do not do this, the vision of the Internet of Things transforming our lives, smart cities and all that is literally out the window, okay? So this is not just a wish, this is where I'm tying a future value to the satisfaction of this requirement. The radio access network, I've moved from being an architect to being a cellular and wireless kind of guy, so I talk in acronyms that are maybe a little different than the architects in the audience would recognize. RAN, radio access network, is the thing that goes between the cellular tower and your phone, okay? Obviously an area of very hot research. It turns out that, or my belief is, that for this vision to be realized, what we've learned from the cellular companies that there will be one radio to rule them all, OFDM, OFDMA, LTE, 5G, standalone, non-standalone, mumble-foo, 3GPP, is the only way to approach the radio problem. That is not true, and we'll explain why that is not true, why that should not be true, okay? And in fact, we should make, just like we made hardware instruction set architectures a non-issue by standardizing on compilers, moving the argument up, the same, I believe, is going to be true for radio access networks. The exclusivity that's associated with OFDM, OFDMA, LTE, all those acronyms, in the world of the IoT will give way to what will eventually be called multi-radio, true multi-radio networks, multi-radio, multi-protocol. And there are good energy-based reasons for claiming that this is so, okay? So the network that we hope for is not your parent's cellular network, which in my view is almost but not quite entirely unlike a real IP network, okay? We continue to benefit from the idea that transistors in the devices are free, and at the low end in the world of the Internet of Things, we can bet on that for a long time. Time has to be a first-order concept in programming. Imagine a programming language where time really is a first-order concept as opposed to a bolt-on. And edge computing and all that we're talking about today, for edge computing, is going to vanish in favor of something that we call edgeless computing. I don't think networks should have edges. I think it's much more reasonable to think about single coherent programming environments that tie together the devices, the computing that we might do in the network and the cloud. But that's the topic for another discussion for another day. Okay? So that's the religion, right? And now what are we doing about it? So in my group, we're taking, not surprisingly, a systems approach to next generation wireless networks and the applications and the programming environments and the core technologies that make up what might be this cyber physical network of the future. So we're engaged in developing a range of sensors, some tools for doing low power programming. I'm going to talk a little bit about that. some real deployments of sensors on road surfaces, applying machine learning both at the cloud and in sensor devices themselves. Think about that for a minute. Where we're going with neural networks is figuring out how to make them much more efficient. I say we, the community, by making them much more efficient, and very quickly we're seeing an overlap between what's possible for computing on a Cortex M3 or some small device that you might put in the environment, and what's required with say a convolutional neural network. There are some neural networks that actually fit, and over time there's going to be acceleration and support for neural networks in sensing applications. Why? Because of exactly what we talked about before. It's cheaper with free transistors. It will be cheaper to do local computation in a device than to try to push bits over a noisy channel. Okay, so neural networks are coming to a dirt cheap sensor near you, and we're exploring that as well. We're also doing some field prototyping. We have a pretty unique environment for doing field-based research. We have an old ambulance that we've turned into an LTE network. I'll tell you about that at the very end of the talk. Okay, so here are a few of the projects that we've got going on in my group addressing a number of problems. So we're looking at low-power synchronization in computing, integrating machine learning into sensing, federating machine learning across dissimilar sensor types. A new project that we just started fairly recently under NSF sponsorship, which is the creation of a language framework that seeks to solve the problems that we've talked about before, and some applications. So I'll go through those in turn, and I'll go through them fairly quickly so that we have some time for questions. Okay. So the first project called LongShot, Long Range Synchronization of Time. Question is, if you're familiar with low-power wide area networks, these are networks that can transmit on the order of 1,000 to 10,000 bits per second using modulation techniques that are robust and resilient against channel noise. Semtech has popularized a scheme called LoRa that uses chirp spread spectrum modulation. Works pretty well. And it's now available very inexpensively from multiple semiconductor vendors, and it's being used as the basis for sensor networks around the world. The question is, and it's been highly optimized for low power mostly off operation. The question is, can we use that as a tool to implement time synchronization in a way that costs asymptotically zero additional power? Okay? Because the classic way of sending packets back and forth over a wireless network, NTP, has its limitations. So we start with that idea and we develop forward from that. So we're looking at a way to achieve microsecond level or tens of microseconds level synchronization at essentially no energy cost, which would enable devices to achieve tight synchronization when they need it, but not run a clock at high synchronization, at high power levels to maintain precise synchronization over fluctuations in temperature during off cycles and so on, okay? Important problem. So here's what we did. We started with a classic algorithm for doing time synchronization over networks, the Network Time Protocol, NTP. And those of you who know the algorithm will be bored to tears, but the basic idea is actually quite simple. If we have two clocks in two devices, the end device and a gateway, and our objective is to synchronize the end device's clock to the gateway's clock, and we have a network that connects us, what we do is we make four simple measurements and we do a computation. We send a packet from our end device to the gateway. And when we send it, we record our local time based on our local presumed incorrect clock, call that T0. When the packet arrives at the remote gateway, at the instant that the gateway receives it, it records the time of arrival based on its clock. And then it might do some processing before it sends a reply packet. But it sends a reply packet, and in the reply packet, just as it's going out the door, it stamps the packet with the time, the then current time at the network server. And when we get it here on the remote device, we record the time according to our local imprecise clock. And with a little bit of math, we can compute the offset between these two clocks by estimating the network delay, right? We know how long in our clock it took between when we started and when we finished. That's the round trip time. And we know if the server sends us T1 and T2 in that packet that it replies with, we can figure out how much time the server sat doing nothing. That's the network server time. If we subtract those two, The difference is the transit time, okay? Now, we make a big assumption. We assume the transit time is symmetric, and we divide by 2, right? And having divided by 2, we can then take the time T2 that we got in the packet from the server. We can subtract the one-way, the divided by 2 round-trip time, and we now know that when our clock said T3, we can figure out what the service clock was. We can set our clock accordingly. And in principle, this works really well. In practice, you know what Einstein said about the difference between theory and practice? That in theory, there's no difference between theory and practice, but in practice, there is. So in practice, when we run NTP, we run into all kinds of problems, right? In an IP network, these links are rarely symmetric, and we rarely can figure out what they are, okay? We can do lots of trials, and we can do statistical aggregation, and if we do it fast enough, we can make some assumption about what the error must be given the rate at which we sample and the rate at which the network routes change and so on, okay? Now, let's take that same idea and apply it to this El Cheapo signaling network called LoRa. We'd like to do exactly the same thing, right? We'd like to send a packet to the server, have the server respond, and then do the computation. Well, what do we have to deal with if we do that math? It turns out that we're running very slowly, right? We're not sending a packet every millisecond. We may send a packet over the span of seconds, right? If we send two packets, they're going to be seconds apart. During that span of time, we have to deal with the fact that this dirt cheap clock in our 50-cent sensor that has a 3-cent resonator instead of a decent crystal oscillator will have drifted, okay? NTP algorithm doesn't account for the fact that the local clocks or the remote clocks will drift. The second thing that we have to concern ourselves with is these delays are actually a function of physical distance, right? So we have to find a way to solve for the distance, the network delay, and for the drift, okay? Well, I won't belabor it. If you actually dig into it, which we did, every single operation that the chip does in sending a packet, marking it as having been sent, has to be reverse engineered. So we very carefully looked at what information do we get from the chip when it transmits, how can we deduce when the tail end of the packet has in fact left our server, right? When Elvis has left the building here, T0. And when did it get to the server, and how do we know? So this is some good hardcore lab work, which we did. And it turns out that the data sheets don't tell us exactly what we need to know, but with the chips as they exist today, they're pretty deterministic. Thank God for state machines, okay? So it turns out that if you look, for instance, at the power amplifier output on the transmitter, you might see something like this. But the report that the transmit signal is in fact done comes significantly later, okay? If you probe the power as a proxy for when the actual transmitter is turned off, you see yet a different story. But it's all very deterministic. So with a little bit of work, we can figure out what the time is between when we are told that the transmission is complete and when the transmission was actually complete, okay? And with a fair amount of work, we can do the same sort of thing on the receive side, right? Here's the incoming signal. There's the interrupt that says, yeah, we've got the packet. But that's not what we want. What we really want is the event that happened back here when we finished receiving the packet, okay? Well, we can back that out too, all right? And so with some good lab work and a little bit of math, we can actually do this. And it turns out that if we study it across some different distances and across temperature ranges and so on, we can do pretty darn well. And in fact, we're getting results that are, so if you look at the bandwidth of the signal, which is a proxy for how accurately you can use the signal as a signal for time, about 10 microseconds. 10 microseconds is about as good as you can get with a 125 kilohertz wide signal. And we are, the errors vary, but we're very close. We're very close to the theoretical limit, and we're doing it with just 2 packets. And in fact, we can piggyback this time probing on regular traffic, right? So we essentially get accuracy down to about 10 microsecond synchronization for cheap devices using essentially no additional power from the battery, okay? Works great. Now, what does this say? So it works great for this chip under the circumstances that we simulated it. What is the lesson that we really learned from our research perspective? It teaches us that for the chip manufacturers, they're actually exquisitely close to exposing this as a function that's tremendously valuable that costs almost nothing. And if they either publish the delay figures that we had to go reverse engineer, or better yet, they put the clock in the chip and do the timestamping in the chip, then we get all that benefit for essentially nothing. You might be familiar with the precision time protocol, IEEE 1588. We borrowed some ideas from 1588 to do this, but it works, okay? And it costs essentially nothing. It gets us closer to the goal of precise synchronization in this distributed world of the Internet of Things, where energy is so precious, okay? We've also built some tools. One of the things that our campus is known for is software engineering. We turn out a phenomenal number of really high-quality software engineering grads every year. And guess where they go? They go to the G company and the F company and the L company, where you ask them about the economics of the program that they wrote, and they sort of scratch their head. What do you mean the economics? Well, how much power does it take to run your program? I don't know. Yeah, well, how much? So if you then take those same students and you plunk them down in an embedded systems course, where all of the resources have constraints, right? Memory is limited, computing capacity is limited, most importantly, power is limited. What do, right? They don't know from first principles what to do. And exactly, right? They have short necks and flat foreheads, because you ask them a question, they go like this, you tell them the answer, and they go like that. So what we can do, what we have done, is to provide tools to let the power be made manifest, okay? This is not something you can do easily with an oscilloscope. So what we did was we built an instrumentation system. Actually, we built a device that's a proxy for a whole host of sort of low-end SoC-based Internet of Things sensors, not in form factor, but in terms of the processor. This uses an ARM Cortex-M3, which is not a slouchy processor, but it's not 8-bit either. It's a real honest-to-goodness 32-bit processor. And by the way, did I say, imagine that in this future world where we have sensors being shared widely in the smart city, every sensor is going to be shared by multiple different applications. Read multi-tenant. Read, it's probably going to be running Linux, and it will probably have different security partitions and so on. So we will have data centers in these little devices that sit on the pavement for information sharing reasons, if nothing else. So we built a device that's a proxy for that. It runs FreeRTOS, which is a nice El Cheapo, but good real-time operating system that supports queues and semaphores and process scheduling. It's a preemptive multitasking operating system. So we built that device. And we put a bunch of sensors on it. I mean, it's the form factor of this phone actually, surprisingly or not surprisingly, looks like an iPhone 6, which is when we developed it. It has a camera. It's got Bluetooth. It's got Wi-Fi. It actually has a slot which we've now put a LoRa radio onto. So this is actually a great device for prototyping Internet of Things sensors. And we teach 3 classes at CMU that use this prototyping device to teach the principle. But the punchline is this. We've designed the power subsystem for PowerDue such that the processor, the sensors, the actuators, and the radios are on 4 separate power domains. And each one has a power meter. And on the back side of the board is another processor that does nothing more than read those power meters synchronously and report them to a tool that we've created. You can't see it terribly well on the screen here, but it's essentially a 4-channel oscilloscope that is showing the power per channel. But it's not just per channel. We actually have the operating system for FreeRTOS and the front side processor, where your code goes, in cahoots with the instrumentation processor, so that every time a task switch occurs, it's whispered to the instrumentation processor. So now the instrumentation processor can not only tell you what the processor power is, it can say, here's task 7's power, and here's task 3's power. And an amazing thing happens when you put this in front of students. Amazing thing. Power optimization by 3 orders of magnitude almost overnight. Really, it's amazing. When you show students this, they say, that task shouldn't be, oh, it's doing a busy wait. Yeah, I can fix that. And all of a sudden, brrr, we have low power software. And very successful. Yes, question?
First thing I did when I looked at that, I want spare FPGA gates for that.
Well, so we could very easily do a new version of this with Zinc on it. The one thing that I really would like, and I don't know if maybe you can tell me, As far as I know, the first versions of Zinc and the board, the dev board that it came with, had exactly one sensor resistor for the whole processor. And what I want is the ability to monitor the FPGA fabric or chunks of the FPGA fabric separately, so that I can put different hunks of logic in different parts of the fabric and monitor the power. So we can talk about that. But
you design circuits on it that give you some of these analog.
yeah. I mean, there's a whole host. Well, given this, I put this up in front of people and say, oh wow, yeah, that's yes, a tool for low power software engineering makes sense. So we built this 3-4 years ago, and we now use it pretty consistently in class, and it has the intended effect, which is helping us write low power software. I want to switch gears and just really quickly hit a couple of other projects that are in this SMILE domain, and then tell you a little bit about our kind of unique research environment that we have at CMUSV. So we also are actually very interested in multisensory learning, meaning that we have many sensors in the environment and they can train one another. Okay, so we actually did a project where we have, I'm going to skip pretty quickly through this, where we have, where we asked the question, first question is, if we put sensors, if we want to put machine learning in a sensor device, how do we train it online with minimal human intervention? This was motivated actually by a problem of having a drone track Andy when it isn't trained a priori to recognize Andy when it takes off. So we started with a basic image recognition fabric, and then built a system that let us do real-time learning and classification with a ground operator that would get Andy in view and then click on Andy's image. And then we did an interesting thing. We realized that if you have a drone that can move, and it moves even if you don't want it to, and Andy's going to move around, the training events, the real-time clicking on Andy's, are expensive, right? If we have a soldier in the field or an emergency services worker who's looking to track somebody or whatever, having that person repeatedly click, click, click every time he sees Andy in the image, and then eventually the drone says, oh, okay, yeah, now I know how to recognize Andy, I'm going to go get him. But it took 57 training events, 57 clicks to do that. No one's going to use such a system. But it turns out that unlike the sort of historically, the image recognition neural network experiments have focused largely on corpora of static images. You train on this set of images, you test on that set of images. Well, video is a different beast. Video is a really different beast. And in video, the premise is that image 2 is not really all that different from image 1. And guess what? Getting a neural net or even sort of classic signal processing to say, oh, you clicked in this area, well, I'm going to segment that from the background over the span of a couple of images. Or I'm going to do something really simple like pixel tracking or image flow, optical flow, based on the movement of the camera. And what I can do then is frame number 2 can become another training example for my neural net without the operator actually clicking, right? And it turns out that that works really, really well, okay? Click once and then do some basic object segment, foreground, background segmentation and object tracking. And the device itself that's learning can take image 2, image 3, image 4, image 5, image 6, where Andy's moving relative to the background as training images. And the fact that he's moving means that they're actually really pretty good training images. It learns which pixels are constantly associated with him and which ones aren't, okay? That's the ClickBAIT project. I love this name, ClickBAIT. Click-based accelerated incremental training, ClickBAIT. So we did exactly that. We built a system that uses object tracking and has a simple user interface for interpreting clicks from a user. Apologize for the spacing thing here. And it will learn and track an object actually very effectively with quite few examples. And without boring you, we developed a metric called incremental training benefit that lets us identify and measure how much value there is to each training event, okay? And what we're after is lots of training with few clicks, right? And using this incremental training benefit metric, we're able to demonstrate pretty robustly that using drone imagery and other imagery, you can use static cameras as well, we can get 5 to 7 times improvement, meaning a neural net that has the same recognition accuracy with 1/5 to 1/7 the number of click events. Okay? That's pretty good. Okay? But that's not where the story ends. We then said, in a search and rescue and a campus surveillance, whatever application, there will be multiple sensors. We made that point, right? Multiple sensors. And they are dissimilar, but maybe they both can learn, and they can learn from each other while they're individually learning. So we built a system, again, not to belabor it, I'm not going to go into the details, that starts with the premise that we may have a bunch of cameras in a smart city and a bunch of our CMU traffic sensors. And we postulate that the camera has this ClickBAIT capability that if you give it a trigger, either from a human or something else, here's the image, learn from it. It can look at, as the object drives through the frame, it can get multiple training events just from that, just from a trigger. But the trigger doesn't have to come from a human. So for instance, let's imagine we have some area where someone's not supposed to be driving. Our little pavement sensor here detects that a car has just driven over that spot. It triggers the nearby camera, and the camera starts learning. Okay? Well, okay, that's kind of obvious, and that's not hard. But here's the interesting bit. We learned that if you go down this path, I'm going to skip some of these details. I'll have them in the slides if you're interested. Our little traffic sensor uses a 3-axis magnetometer. And we spent a lot of time looking at the traces that come from this magnetometer as cars of various sorts drive over them. And we learned a really interesting thing. And I could perform this experiment with you. I don't have the slides here today, but we could perform this experiment where I show you 10 different magnetometer traces from 10 different vehicles. And then I give you an 11th one from a vehicle that's in the set that's driving at a different speed, and you'd be able to tell which one it was. Okay? So it turns out that with a little bit of neural network technology in the device itself, we can train it to deconvolve a vehicle's speed and a vehicle's type. Okay? By learning the magnetic signature, right, you can correlate and figure out things that you wouldn't know just from the triggering that typically magnetic sensors in this domain are used for triggering. We're using them for learning the signature of a vehicle. Okay? Now connect those two together. When we see the vehicle drive over the sensor, we have now evidence of its magnetic signature and its image. But we don't know for sure which one is which. But we can correlate them. And the next time we see that pair, we reinforce that. If we now see the vehicle on a magnetic sensor that doesn't have a camera nearby, we can match it with the image of the camera that we learned because we learned to match the signature of the camera with the signature of the vehicle. Okay? So multisensory learning, self-reinforcement, actually works. And then in this domain, the last thing that I'll mention, once you figure out how to take the number of clicks that it takes to train somebody, to train an on the drone neural network to recognize and track a target down to almost nothing, down to maybe just a trigger that a human doesn't initiate. Now the question is, can we further extend that by one time clicking on the image of Andy that the drone can see and having the drone do what a 4-year-old would do? You take your 4-year-old granddaughter to the zoo and you say, that's a lion. What is she going to do? Is she going to just stand there? No, she's going to run around the cage and look at it from different angles and stand there long enough to watch it move and form a model in her mind of what the animal looks like. Okay? Can a drone do that? Well, it turns out that it can't. And what we did was we created, so the hypothesis is we're going to create a system in the drone that not only does object tracking and segmentation to train a third neural net to recognize Andy, our Andy detector, we're going to have a fourth neural network that's trained offline in the principles of how to move in order to learn. So we created some synthetic environments of objects that we want to track and occluders. This is a photorealistic, an environment that's capable of photorealistic simulation with physics. You'd bump into something and you crash. Okay? This is a tool that we created called Viper, the Virtual Image Processing Environment for Research. Interesting thing here is we can train drones in faster than real time. It's sort of like the Matrix, right? You know, Neo goes into the Matrix and learns Kung Fu without actually having experienced it. Well, we have sort of a dojo like that for training drones. So in this particular experiment, we present the drone in simulation with a variety of physical situations, right? It can move in three-dimensional space in simulation. So when we say, what we're really trying to do is to train you to recognize, build a mental model, if you will, of that purple block, move around and get an idea of what's going on. And as it moves, it will learn to associate different kinds of moves with goodness and badness. It learns to associate occluders on the right and the left with things that will block its view if it moves in those directions, okay, without being explicitly told. So across many virtual environments and many scenes, we score the neural network on how well it learns. We penalize it for asking questions, and we reward it for being able to recognize after a training sequence that it's done well. And so, you know, like any reinforcement learning, gamified system, it just plays the game thousands of times and learns how to move to maximize its ability to learn. And then we apply that in the real world. So we take that same neural net that has learned to associate the object of interest with potential occluders, and we put it in a drone and we let the drone fly. What happens? Well, let's see. So it's a little bit jerky, and it's maybe hard to understand from what's going on here. But here's a simulated world where the drone is learning and being scored in real time with, should it stand in place and take more images so as to reinforce its knowledge? Should it move left? Should it move right? Should it move over the object? And it has developed over experience scores for which moves produce the best learning. We turn it loose in the real environment, and guess what it does? So this is my student, Irvin Tang, was the one who was the prime developer of this technology that we call autonomous curiosity. We were down at Camp Roberts, which is a military base, flying drones. We can fly there safely using the facilities that we have. It was a wonderful moment, and I wish I had it on video. Irvin was flying this drone, and he launched it and got the image of a car that he was trying to train it in the viewfinder. It was actually trying to train a car that was on the other side of this building here. So the drone's up there, and he manually launches it for safety, puts it in position, and then turns on autonomous curiosity. And the drone does this, and it does this, and then it does this. Runs around to the other side of the building. And he just was dumbfounded. I said, what's wrong? He said, I designed it to do that, and it actually did. He was so amazed that it exhibited this notion of curiosity, and blocked objects are something to be avoided, and it should do it quickly because we trained it. One of the metrics is time, which is a proxy for battery power in the drone, right? So loitering is...
He didn't have a younger sibling, I think.
No.
Otherwise he would have...
Yeah. Exactly. I have a granddaughter now, so I'm... Yeah. That's a great way to appreciate what learning is all about. Anyway, to make a long story short, we benchmarked that against a number of different flight strategies, sort of random, pick a left, right, up, down direction, or always go left, or orbit, or whatever. And the offline learner consistently outperformed the random strategies, which I think lends credence to the idea that this notion of curiosity can be taught. It can be captured in something that can then be reused. Okay, I'm going to skip this. And the crowdsourced traffic sensing. We're doing a project with the U.S. Geological Survey where we're actually deploying some of these ideas in the field. And that's sort of a theme for another day. One thing I do want to talk about before we close is a lot of what we do. I'm an experimentalist by nature, and I drag my students, sometimes screaming and kicking, out to the field. We'd go down to Camp Roberts 3 or 4 times a year. Sorry?
Make that feet dirty.
Exactly. You've got to get dirt under your fingernails in this domain, right? So this is, as I said, is a domain that really lends itself to experimentation in terms of surfacing the interesting hard problems rather than just doing cool demos. So we created an environment that lets us do these experiments well. All of our experiments typically involve something that moves like a drone, lots of radios, reconfigurable to different protocols and so on, some cellular, some not. And we're in a very austere environment where there's no power, there's no nothing. So we bought an old ambulance. Used to belong to LA. It was red in its original life. It got repainted as white. We refitted it with a 42-foot pneumatic mast, put in a rack full of equipment. So we've got a whole stack of software-defined radios and some sort of private local cloud servers, as well as a number of radios and a SATCOM unit that let us connect to the internet from wherever we're at. It's this wonderful and uninterruptible power source, right? That's got a diesel generator, a gasoline generator, 3 big marine batteries, an inverter. So we can really run off-grid pretty substantial, and in comfort too. It's got a ton of air conditioning in it. It's a wonderful environment. That's a jack on the side that lets you plug into the, it comes from boating, right? This is what they call the thing that you plug into when you bring your yacht to Nantucket Harbor. You plug into shore power, okay? So that's our ambulance, and it's actually served us amazingly well. I was going to bring it today. We had some difficulty in finding parking space for it and so on, but you're all invited. Those are watching by video as well. If you're actually interested in sitting in it, Eugene has been in it and can attest to the fact that it's pretty cool. But it's kind of a Swiss Army knife for radio, neural network in the field, Internet of Things, sensing research, and we make pretty heavy use of it. Okay, it's also a really great 11,000-pound counterweight for when we use it for amateur radio. So this is a 4-element beam with a 32-foot boom and a 36-foot span. Our pneumatic mast will hoist 150 pounds. That's a 100-pound antenna. So we use that for amateur radio field day. Literally, we go from 1 megahertz up to 6 gigahertz with this van. It's a fantastic resource.
Not with that antenna.
Sorry, not with that antenna. All right. So now this antenna will do, is designed for 10, 15, and 20 meters. This is a really cool antenna. These are fiberglass poles, and inside them is beryllium copper tape, sort of like tape measure tape with motors. And as you change the frequency of the transmitter, the elements move in and out to make a nearly perfect 1-to-1 standing wave ratio match. So wonderful antenna. But that's another story. So one thing I have to show you, and for the sake of copyright, I couldn't include the images that I wanted to. This van, in some spiritual sense, traces its roots back to the SRI bread van. Anybody remember the SRI bread van? Good. You can see it at the Computer History Museum. It's under a tarp there. But I put these pictures in here for our image. This is Don Nielsen, who was one of the architects of the bread van. And this is Vince Cerf, also one of the architects of the early internet. And there's a picture that goes along with this that for copyright reasons I did not include in my slides, but nothing prevents me from bringing up a web page. Here's the bread van and a much younger Vince Cerf. So knowing this picture when Vint visited, Vint's an old friend, when Vint visited, I had to have him come and do a stand. He had a pose for a picture with the Cross Mobile van. So just to summarize, I think the IoT brings some really interesting new opportunities and hard problems that call for a systems approach. We've talked about the power, programming, federation, and timing as interrelated problems. We also mentioned the idea that networking can't be cellular, and I didn't go into that in depth, but the primary reason is that cellular imposes a very high energy tax for protocol overhead. We can have a separate conversation about that. LPWAN networks are free of that. They have some other downsides to them, but device-centric networking is really the difference between what we're doing and cellular attached devices. This domain is very, very well, it benefits from the idea of study, develop, deploy, evaluate, sort of lather, rinse, repeat, and that's what we're all about. And that's it. That's all I've got for you today.